Convection, physics of convection, convective parameterization are all very detailed, complicated, and intricate topics. I won't even pretend to be an expert, but to give you a complete context, I'm going to include this podcast from the same book as in the last podcast, just to highlight a few of the issues and show one or two parameterization schemes and the kind of details that go into them. So here is a radar depiction of mesoscale convective system with both convective and stratiform precipitation and isolated convective cells and stratiform rain along a frontal boundary. The convective region is associated with stronger updrafts, higher reflectivities, and more vertically oriented cells. The stratiform region is associated with weak updrafts, lower reflectivities, and sometimes is composed of remnants from previous active cells from the convective region. So to begin with, you have to just know that convective and stratiform rainfalls processes are very different. Convection you can think of as forced ascent, dynamic ascent, where you have instabilities that are demanding moisture, converting into precipitation and sucking up moisture and have stronger updrafts, whereas stratiforms typically form around air that is gently rising over topography, or they are flowing out of the strong convective updrafts of the convective systems and so on. So that's things to remember, but also note the strong juxtaposition of convection, stratiform here, and convective cells or mesoscale convective systems. So keeping in mind again the problems of orography, resolution, and basic physical understanding, and then remembering that having to resolve these different forms of rainfall formation and convection, one is going to face lots of different aspects. So here, schematic showing a unit horizontal area, for example a grid cell, at some vertical level between the cloud base where the air is rising and hitting the cloud base, and highest cloud top here. All the clouds are shown to entrain environmental air at each level, with detrainment occurring at the top of the cloud. Okay, the smallest cloud pictured has lost its buoyancy, and at this particular level is detraining cloud air into the environment as shown by the outwardly directed arrows. So here you can see that entrainment is happening into the cloud, and there is at some point detrainment happening. You can see here a cloud that has lost the smallest cloud has lost its buoyancy, so it cannot rise anymore. There is no condensation heating creating buoyancy and allowing it to rise anymore, so that it can entrain air and continue to entrain environmental air and continue to grow or extend. So you can see the different kinds of clouds as well. You have things like cumulus clouds, which are not rain-bearing clouds. You have deep cumulus clouds, and this is the different number of clouds carried in the model with different properties. So this is how Arakawa-Schubert scheme looks at data. Basically, it has an environment in which deep convection happens, and there are various processes happening in terms of moisture fluxes and detrainments, and how the environment adjusts to the convective processes, so that overall grid level properties can be written in terms of the parameterization. I won't say much more than that. The details of how these are done are very different, as we will see in the Allen-Bethe scheme, which goes into hairy details of the processes that occur during the cloud microphysical processes. This is from Brian Mapes, the time series of imposed mesoscale convective system like heating in the black line here. linear stepwise distribution from MAPE's linear model and area integrated values of upward motion as sampled by synthetic low latitude Robinson arrays with 500 and 1000 kilometer diameters. So the data itself can provide different evolution of the heating associated with convective systems, but Brian Mapes basically parameterized them by using data and putting it in time as a stepwise function of heating, which can then be fed into a circulation model to study other processes like where the rainfall happens, how much happens in the anvil versus how much happens in the convective plume, and so on and so forth. So you can see the anvil here. I think one of the major results from Brian Mapes is that these regions, which you think of as spent convective plumes, actually can produce plenty of stratiform rain relative to the convective rain that happens here, for example. Okay, so those are the kind of process details that get parameterized one has to be careful about. Here is a flowchart for Betz-Miller convective parameterization scheme. I won't go into the details, but you can see that find the cloud top mixed moist adiabat. So there is some criterion used to do that. It can be from the data, it's built from the data, but that's how it's done in the model. So then it can generate shallow and deep convection, can compute reference mixing line, correct to satisfy the thermodynamic moist and dry static energies, adjust the profiles of temperature and humidity with some time scale, and feed it to the large scale model. In the deep convection, it's computing reference quantities like moisture, water vapor, and specified downdraft boundary layer, again correcting to satisfy the energy requirements, produce precipitation. If precipitation is greater than 0, then it changes the mixing line. So there is a shallow cloud top layer, so there is an interaction between shallow and deep convections here. Adjust again temperature and humidity profiles and feed it to large scale circulation, so that the dynamics or the circulation and the thermodynamics or microphysics are closely coupled as observed. And this parameterized convective rainfall from the Betz-Miller, this is the modified Betz-Miller scheme here, as a function of relative humidity changes in the cloud layers. So how to convert the convection itself into precipitation requires certain assumptions as well. So scheme of rainfall in centimeters, change in cloud layer, relative humidity. So you can see how dramatically the rainfall amounts change. So there is no fundamental equation which is driving the process from the evaporation to rising air, expansion, condensation, cloud formation, convection, etc., etc. There are many parameterizations involved. So convective parameterizations tend to be still the most difficult, complicated aspects that produce dramatically different results in models. And even when one model is doing systematically better than another model, it's not always easy to pinpoint to say exactly what in this model is doing better than this model and simply transpose that solution into another model, because there are many modules like the dynamics core, microphysics, radiation, and so on and so forth. Other aspects to worry about: atmospheric flow patterns over three-dimensional hill so it's the orographic drag that we mentioned before, neutral stratification, weak stratification, moderate stratification, and strong stratification. So the form drag and the orographic drag themselves tend to depend on the flow regime you are in. So there is some flow dependency of how the orography affects the flow over the orography and what happens on the downstream side and so on. Again, I won't go into it details, but stability of the vertical profiles, how much humidity there is, etc. And how the orography gets represented itself depends on the resolution, as we saw in the case of Hawaii. So this is just a detail schematic of normalized surface pressure drag as a function of Froude number for constant values of Brunt-Väisälä frequency, static stability, and U, the velocity, that outlines three flow regimes identified from numerical simulations. So there are large-scale eddy resolving models, or so-called large eddy simulations, and so on, which are done to derive some of these parameters that are then translated into full models. Pressure drag is normalized by value expected from linear theory due to freely propagating gravity waves. So gravity wave drag is a very critical parameter as well. Normalized surface pressure drag, so you have linear wave dynamics, non-linear wave dynamics, and near surface flow dynamics together, determining the inverse Froude number that is done carefully with very high resolution large-scale eddy simulations, and so on and so forth. So as for the future, here is the example we have seen before of the chaos that ends up creating solutions getting unreliable very quickly in a weather model. So 2 points are starting here very close to each other, but very quickly they can end up very, very far away from each other because of the intrinsic non-linearities of the system, which we called the Lorentz-Salzman model, typically referred to as the Lorentz model. And we looked at the coupled equations in x, y, and z, and we are showing the solutions here again. As we have mentioned before, these have certain properties with strange attractors that don't cross in the xz and yz planes, and so on and so forth. In reality, you can see such a thing happening here. So this is a spaghetti diagram, or multiple solutions evolving from a forecast system. So this is looking at 500 hectopascal geopotential height isolines from a particular short-range ensemble forecasting system, which means initial conditions are perturbed and forecasts are made for a certain period. So this is starting on 9Z 22nd August, and we are looking at 24th August as solutions. And all I will say is that small differences end up producing some solutions that are smoothly going over the continent across, whereas some are producing a ridge or an anticyclone to develop. So you have to be sure that your ensemble system is got enough range of solutions that you can issue reliable forecasts each time. The fronts can be displaced, forecasts can be correct, but front can be displaced, and so on and so forth. So instead of snowing here, you might still get the same amount of snow, but it's displaced by 50 kilometers. People here are going to be very disappointed because they were waiting on a snow forecast of let's say 10 inches. They closed schools, they got ready with salt spraying on the roads and everything, and so on. So these are very critical issues. How to reduce these kind of situations for the future are some of the things being looked at with techniques like improved initializations with data assimilation, improved data coming in with drones and radiosondes and balloons and satellites and other things, aircrafts, and also using artificial intelligence, deep learning, machine learning. All kinds of techniques are being used to resolve the nonlinearities that are very intrinsic to the system and can never be completely removed, irreducible uncertainties. So no matter how much we improve our understanding and models, there are going to be these irreducible uncertainties which have to be dealt with. So another example is the cloud scale model prediction here, and observed radar reflectivity fields valid for 0100 universal time 11th May 2005. While the cloud scale model clearly captures the typical types of reflectivity structures seen in observations, the model has clearly missed the thunderstorms active in Nebraska and Iowa and misplaced the convection in Minnesota in the upper right portion here. southwestward, image created as part of the Storm Prediction Center. So as I said, the forecast may call for some activity in snowfall or sleet and so on here, whereas the observations show that it is way off for Minnesota and for Nebraska and Iowa and so on and so forth. So tough business. So now there are cloud resolving models, cloud scale models, and so on. They tend to have very high resolution, high computational cost, and yet you can see such errors. So parameterizations, there are so-called stochastic parameterizations now, where the nonlinearity of the system are captured in the parameterizations themselves. There are many details there. I'm just using the words in a very casual sense, but there is very good literature on stochastic parameterizations as well, which capture the nature of the stochasticity in the system itself. Okay? So they are not deterministic parameterizations like the convective parameterizations that we used. So Tim Palmer and there are many other people now looking at stochastic parameterizations as a way forward to do these things. So lots of things going on. Artificial intelligence, stochastic parameterizations, improved model resolutions, cloud resolving models, explicit convection, and so on and so forth, that you can read up if you are interested in them. This is a very brief introduction, so just take it for what it is, okay?